go back over what we kind of worked on before, just so that we understand this and kind of prepping us to move into the next thing that we're going to learn. So back a few weeks ago, we learned about the central limit theorem, CLT, central limit theorem. What did that tell us? That told us that if I have a population and the mean of the population is mu, let's say it's equal to 100. And I have that population, the variability in that population, the standard deviation, is equal to 10. Well, if that is normally distributed, it might look something like this, where the middle of the population, the mean and the average, is 100. And then 95% of the people in this population are between roughly 80 and 120. In other words, 95% of the subjects or the measurements in this population are within 2 standard deviations of the mean, if it's a normal distribution. So now, one of the things that we've learned is, we're almost never going to know the mean and the standard deviation. So we're almost always going to be working from samples. So when we work from samples, we want to understand the dynamics of, if we take a sample of size 25, right? Take a sample of size 25, what is that going to look like compared to the real population when we look at it in terms of the real population? So I sampled 25 people randomly from this population, and I find that the average for those 25 people is 102, let's say. And the standard deviation of that sample is, let's say, turns out to be 12. Well, it's not exactly the same as the population, but it's pretty close. In other words, the mean of our sample approximates the mean of the population. That's the whole reason for taking a sample, right? And often the standard deviation also approximates sigma, the standard deviation of the population. Right? So that's the whole point behind taking samples, because otherwise we wouldn't really ever know anything about this population, because we're almost never gonna actually measure an entire population. So one of the things that we noticed, one of the things that we learned, is that if we take repeated samples of size 25, in other words, take 25 people randomly, find the average, write that down, take another 20, let's say it came out to 102, take another 25 people, comes out to 99, take another 25 people, the mean comes out to 103, take another 25 people, mean comes out to 100, another 25 people, 101. If I keep doing that thousands of times, I'm going to find that the distribution of these sample means is going to have a relationship to the population distribution. Number one, the mean for our sample distribution is going to be the same as the mean for our population. In other words, half the time we're going to be under 100, half the time we're going to be over 100 when we take a sample of 25, right? And the standard deviation is going to approximate the standard deviation of the population divided by the square root of n. Well, wait a second, what happened there? Remember up here when I took a single sample, standard deviation of the people in that sample. Well, this is different. This is if we took this average of all of these 25 people, if we took the average over and over again, the standard deviation of that distribution now of these sample means is going to be smaller, because if you can imagine, if the range of people is from 80 to 120, if I take 25 of them, the average is going to be close to the middle. It's going to be close to 100. And if I take another, it's going to be close to 100. So it's not going to be that. So the variability here is going to be narrower than the variability of the population. Well, what is it going to be? Well, if I look at this, if I know the population standard deviation, sigma, if I had known that, I could say that the standard deviation for our sample means is going to be standard deviation, the sigma, over the square root of the sample size. So if sigma was 10 and the sample size is 25, right, it's going to be 10 over 5 is going to be equal to 2. In other words, 95% of my samples are going to have a mean between 96 and 104. A lot different than 80 and 120, right? Okay, that's the idea behind this idea of central limit theorem. This tells us that this is what's going to happen when we take repeated samples. Well, what if my sample size was 100? Well, then sigma over the square root of n is going to be equal to, it's going to be equal to 10 over 10 is going to be 1. So my distribution is going to be even narrower if I increase the sample size, right? So we can take advantage of this property to understand how, when I take a sample of size 25, how likely it is that I'm going to be near the true mean of the population. And what do we do with that knowledge? What we did with that knowledge is we learned how to calculate a confidence interval. Okay, so for instance, we found that if we knew sigma, if we don't know what mu is, right? That's unknown. If we knew that sigma, and this is an artificial situation, if we knew that sigma was equal to 10, if I took a sample of size 25 and I took 25 people and the average came out to be equal to 101, right? And sigma is equal to 100. Well, if I take repeated samples, sigma for samples is going to be equal to my standard deviation for samples. I'm going to give it a new name. I'm going to call it, instead of standard deviation, I'm going to call it standard error. Okay, that's going to be equal to sigma over the square root of the sample size. So standard error is going to be 10 over 5 is going to be equal to 2, right? So I can say that, gee, my mean came out to be 101, but my expectation is this is going to represent the variability for the population, the samples from that population. So I can throw together this idea that whatever I get as my X bar, if I add and subtract 2 standard errors from it, I'm 95% certain that I will get the true population mean between those 2 numbers. Okay, so now not only do I know my sample mean is 101, but now I can say that my true population is 95% certain to lie between 2 times 2 is 4, lie between 97 and 105. Well, that kind of helps me quantify this. In other words, if I do a study and I write in my abstract that the average blood lead level for children in the Bronx is 6.07 micrograms per deciliter, right? If I write that the average is equal to that, right? Well, people look at that and they say, well, what size sample was it? How accurately did he know that? And if I now can also say that the confidence interval, my 95% confidence interval, is that it's between 4.01 and 8.08. Now I understand that, yeah, in my sample, that's what I got. But the variability of this suggests that I can be 95% certain. Well, I don't know. All I know is my sample mean. So I could be underestimating the true mean or overestimating it, but at least I know with 95% certainty that it's between these 2 numbers. It helps me understand how well I know the true population mean. So for instance, if I told you that the mean was 6.07 with a 95% confidence interval of 5.5 to 6.5, okay, or I gave you 6.07 with a 95% confidence interval of 4.0 to 8.0. Well, which of those 2 would you prefer? Yeah, no, the top one, because that tells you that your sample size and the variability of the information tells you that. So if you're a researcher and you're reading a study, you have more confidence in this than you do in this 6.07 than in this 6.07.
When the confidence interval is narrow, it's more precise.
Well, when the confidence interval is narrower, you can have confidence that it's within this smaller area than if it were wide, right? In other words, if I saw this and if it were important that I needed to know, is it bigger than 5 or smaller than 5? Is it bigger than 5 or smaller than 5? This one helps me because I know I'm 95% sure it's at least 5.5. But this one doesn't help me that much because I'm not 95% sure it's more than 5. It could be 4 or 4.5, or, so it could be inside that 95% confidence interval. So it helps people that are reading your study understand what that 6.07 really means. In other words, is that something I can rely on being close, very close to the true population mean, or, I got to give it a little bit more leeway then. But in general, as your confidence, 95% confidence interval, if that's 5 to 10, right? If you want a 99% confidence interval for the same data, right? Well, then it has to be wider, right? It has to be like 4 to 12 or something like that, because you want it wider, so you higher level of confidence for 95. So I'm looking at two different things here. One is from the perspective of somebody reading the study versus us, who's calculating the confidence interval.
I think when we learn that if you don't have if you don't know the population segment, if you don't know
Right.
the segment, and you use status. Sorry.
Exactly.
No,
You're exactly. I know what you're driving at. Yeah.
You use
The sample standard deviation instead.
Sample standard deviation. Then when you use the T-score, then you have to you want it wider to account for.
That's what the T-score does for you.
Yeah.
Exactly. That's exactly what T-score does for you. I'm going to do that right now. Okay. So the next thing we learned is that that's nonsense. We never know population standard deviation. We never know sigma, right? So what happens? We take a sample of size 25, right? And we know that our X bar, let's say X bar came out to be 101, and we know that the standard deviation of our sample, right? You remember how we calculated that the first week? Standard deviation of our sample came out to be, let's say, 12. Okay, so now I said to myself, okay, so now I want to calculate a confidence interval at this stage. Well, normally, how would I do that? I would say X bar plus or minus 2, actually 1.96, because that 1.96 is a more accurate range for the confidence interval for 95% than 2 is. 2 we got from our estimate using the empirical rule, right? So 1.96 is more accurate. And then for 99, I'll get to that in a second. So X bar plus or minus 1.96. Okay, it's great. So now I got to multiply that. That's 1.96 standard errors, right? In other words, 2 standard errors apart gives me my 95% confidence interval, really 1.96. So in this case, my standard error is equal to sigma over the square root of n, but I don't know sigma. So I am forced to use the standard deviation, which now introduces an extra level of uncertainty. So, but I can use it. 12 over the square root of 25 is equal to 12 over 5 is equal to 2.4, right? Okay, so that's my standard error. So my confidence interval is going to be 101 plus or minus 1.96 times my standard error, which is 2.4. I made a mistake here. What's the problem here? Well, the only reason I could use 1.96 was because I knew my population standard deviation, and I knew that the standard deviation told us the range for 95% of the population, right? Because I knew what sigma was for my population, but now I don't know what sigma is. So instead of using 1.96, I have to use a value that's more conservative than that. I used to have, instead of Z is equal to 1.96 for 95%, I have to use T, which is equal to, and now the tricky part is that for 95% confidence interval, T doesn't have just one value. T has many values. That value is going to depend on the sample size. So for a sample size of 25, right, we have to look it up on the table and find out what to use for, let me find it. Okay, so on this table, if I scroll up here, the first column is degrees of freedom. Degrees of freedom are the sample size minus 1. So it's 24 is what we're looking for. So the sample size 25, I go down to the row 24, and I go across to the third column because the third column represents 95% confidence interval. So 24, so it's 2.06. No, we're creating the confidence interval. Right, we're doing the, yeah, okay. So we want a 95% confidence interval. So instead of 1.96, I'm going to use, yep, 2.064. instead. So I'm going to get rid of that. It's going to be 2.064. Now, if sample size were only 10, that would be a bigger number because we have less confidence in our standard deviation estimating the population sigma with a small sample than we do a big one. If it's a really big sample, like say 1,000 people, then T might be equal to 1.965. So close, it's almost 1.96. In fact, a lot of people with, for a very large sample size will just use 1.96, right? But SPSS, you always actually calculates what T is. Never relies on rounding it to 1.96. So if you want, you can do that too, except it's hard to find a table that'll go up that high, right? So you get pretty close. I think 100, sample size of 100, the T value is 1.98, I think. 100 or 200, one or the other. Okay, so what do I do now? I take my 101 plus or minus 2.064 times 2.4. I'm going to estimate that to be like 4.9. I'm just doing this in my head real quick. So that's going to be a confidence interval of 105.9, and on the other end is going to be 0.1 is 96.1, I think. All right, so I'm 95% sure the true population mean is between these two numbers based on that sample size, this standard deviation, and this mean. Right? That's how we do our confidence interval. That's where our t-score comes in. So now we took this one step further. Okay, the next step we took was we said to ourselves, okay, so let's say I take two groups. I take group A and group B, and I take a sample of size 25 from group A and a sample of size 30 from group B. And it turns out that the average I get from group A is 101, and the average I get from group B is 105. Okay, and the standard deviation from group 1 is equal to 10, and standard deviation from group 2 is equal to 12. Okay, so now what do I do now? Well, what I can say to myself is, gee, if I look at the difference between X bar 1 and X bar 2, the difference between those two, what is the difference? It's 101 minus 105. The difference is equal to, say, 4. In this case, negative 4. The sign doesn't matter. The difference is 4. How many it's nice that the difference is 4, but that doesn't tell me anything. What really tells me something is how many standard errors apart are they? Are they one standard deviation apart, standard error in terms of samples, or 2 or 3? If they're more than 2 standard errors apart, more than 2 standard deviations apart, I can say to myself, well, I'm 95% sure that the mean of this population is over here. I'm 95% this population is over here. So, it looks to me, I'm 95% sure that the two population means are different from one another. But in order for me to say that with that level of certainty, with 95% certainty, I have to say to myself, the difference between these two things has to be a certain number of standard errors apart. So I got to take that and divide it by the standard error. Okay, so now my next problem is that, okay, -4, what's the standard deviation here? Well, the standard deviation is 10. Standard deviation here is 12. Different sample sizes. Well, which one should I use? Maybe I can just add them together and use the average. Maybe I can't do that. Maybe I can, maybe I can't. Well, we learned that there's rules for this, right? We had that sheet that we could look this up. And we learned that if the standard deviations, one is not double what the other one is, that we can assume maybe the populations have the same standard deviation and that we can average these two. So it's a weighted average. There's actually a formula for this that we worked on last week. It's weighted average. I'm going to assume they're the same sample size. So it's probably going to come out the standard error is going to be equal to the standard deviation. I'm going to lose 11, right? The average of those two over the square root of the sample size. What's the sample size that I use? Oh man, that's a problem. Let me think for a second here. The sample size is 50, right? Okay, so sample size is 50, right? Because I'm pooling the two of them together. So my standard error is going to be, what's 55? 50 divided by 10 times 5 times 25, 6, 36, 7, 40, about 7. That's about 11 over 7.1, let's say. Right, so this is going to be about 1.5 or something. Okay, these are all rough estimates. Right, standard is about 1.5. So I'm going to take my difference between the two means, and I'm going to divide them by my standard error based on the sample size and pooling all these results together, 1.5. When I divide 1.5 into 4, it comes out to 2.33. Now I have to say to myself, are these far enough apart for me to say that the mean of group A does not equal the mean of group B? How far apart do they have to be? If 1.96, yes, if we knew the two standard deviations, but we don't know the two standard deviations. We have to look up on the T table what the critical value of T is for how many degrees of freedom. We pooled the standard deviations. So it's N1 plus N2 minus 2, right? That's on that sheet, right? Yeah, sure we did. I'll show it to you. Yes, we did. Look back at the video. I'll show you. I'll open the sheet up. We'll take a quick look at it now. Okay, so if I go to my T table, I'm not going to do it. I'm going to say the critical value is equal to 2.03, let's say. 2.03, right? That's critical value. Are they far enough apart for me to reject my null hypothesis that the two means are equal and say that they are different, that the two means are different? Yeah, I exceed. They're further apart than I need them to be. I only need them to be 2.03 standard deviations apart, standard errors apart, and they're 2.33. So I can reject my null hypothesis, right? Now, SPSS, instead of calculating a T critical, gives you a significance or a p-value. And so in this case, it would probably give you a p-value of 0.04. What does that mean? That means there's only a 4% chance that you would get these two means to be this far apart if the population means were equal. What's our level of tolerance for error in this study? Alpha 5% usually, right? Alpha is equal to 5%. So since there's only a 4% chance of having this happen if the two means are equal, you can feel comfortable rejecting the null hypothesis and accepting the alternative that the two means are different from one another.
Sorry, when we did x1 minus x2,
yes,
what did we use?
We used 101 and 105. Oh, yeah. The means of the two samples. Okay?
So when you subtract the two degrees of freedom, it's basically two of the sample sizes?
Yeah, it's the two sample sizes added together minus 2. So like as if you were only going to use one of the two samples, it would be n minus 1. So now you're combining the two. It's a pooled standard deviation. Let me pull up that sheet from last week so that you guys can see this. I'm going to clear this so we can actually read something here. Okay, whoops.
Isn't there a square root over that whole thing?
Over which whole thing?
Over n minus, over n1 plus n2.
No. Hang on, I'm going to get to it. Yeah, I know what you're thinking of, but we'll take a look at if we have the formula in front of us. What am I doing here? Erase all drawings. Let me get my pen back, my pointer back. Okay, so let me go to weekly materials. And last week. And let me go in here. Okay, here we go. Okay, so t-test variations, right? First of all, let's look at this. This is our steps in our hypothesis test, comparing the two means, basically.
Sorry,
Open it.
From the last one, so because 2.33 is greater than T critical, then we can reject.
Yes, exactly, yes. Okay, so because the two means are further apart than we need them to be. That's really what that means, right? 2.3 standard errors apart is further apart than we need them to be in order to reject the null hypothesis. If they weren't far enough apart, we couldn't reject the null hypothesis. If the two means were too close together, we couldn't say the population means were different. Okay, so what are the steps in hypothesis testing? State the null hypothesis. The mu of group A is equal to the mu of group B. Specify the significance level. Alpha is equal to 0.5. Draw a sample size n. Okay, use Z 1.96 when sigma is known. Use T distribution when you have to estimate the standard deviation for sigma. Determine the p-value, the probability of getting that big a difference. Okay, and it's got to be less than 5%, or the critical value has to be smaller than your actual value that you calculate for T. So, and then you can reject the null hypothesis.
So you're using the T value in place of not having
The p-value, what the p is, yeah. Okay, so here's the t-test variations. So, if you are comparing the means of two populations, right? Okay, what are we doing? We're going to calculate T based on the difference between the two means over the standard error. Well, since remember when we were doing a single sample test? When we did a single sample test, we compared the x bar 1 minus mu, the mean that we know about. And we divided by the standard error. And the standard error is calculated by the standard deviation of the sample divided by the sample size, because there was only one standard deviation. We knew the population mean for this other group. We only knew the mean and the x bar and standard deviation for our sample. So this was easy. It was just the standard deviation over the square root of the sample size. Now we have two samples, right? So this becomes a more complicated formula, the standard error on the bottom here. But it's still the difference between the two means over the standard error, this being the standard error. So in order to calculate standard error, first thing you gotta do is calculate the pooled standard deviation. Calculate the pooled standard deviation by the sample size of group 1 minus 1 times the standard deviation of group 1 squared plus n2 minus 1 times standard deviation of group 2 squared over n1 plus n2 minus 2, all of that under a square root sign. So you're right about that, right? So then you wind up with a value for the pooled standard deviation. If the sample sizes were the same, and this happened to be a standard deviation of 10, and this one's standard deviation 11, well, the pooled standard deviation is going to come out in between. It's going to come out 11, right? So it turns out that that's 11 times the square root of 1 over sample size 1 was 25, plus 1 over 25 again. Find the square root of that, multiply by a pooled standard deviation. That's your standard error. Divide that into x1 minus x2, and that gives you your t value. How far apart are your two means in terms of the number of standard errors? If they're far enough apart that you exceed the critical value of t for these sample sizes, then you reject your null hypothesis. X1 and X2 have to be far enough apart that the value of t that you calculate here is bigger than the critical value of t. How do you find the critical value of t? You find the degrees of freedom you need, which for this situation is the sum of the two sample sizes minus 2. You go to the table, look it up, and that's your critical value of t. You compare it to the one you calculated. The one you calculated needs to be bigger than the critical value you looked up on the table so that you can reject your null hypothesis.
And that's always going to be the case, right?
Yep.
Okay.
It's always going to work that way. Now, the next complicating factor is, what if the two standard deviations of these two samples you took are different? What if the standard deviation of group A is 10 and the standard deviation of group B is 25, more than double what the other one is? This one's very variable. This one's not variable at all. What do you do then? Well, then we use a different set of formulas. This is the set of formulas that we use for situations where the standard deviation are different in the two groups. Okay, and that's usually when we're doing it seat of the pants, when we're doing it by estimating it, we're saying if the difference is of one standard deviation in group A is twice the standard deviation of the other group, we're going to assume that they're not the population standard deviations are not equal, and we're going to use these formulas. If they're closer, like not more than twice what the other one is, then we're going to assume them to be equal, and we're going to use this first one where we pool them. So in this one, we say that t is equal to, no surprise, x1 minus x2, x bar 1 minus x bar 2, over the standard error. But this time, the standard error is the standard deviation squared of group 1 over the sample size of group 1, plus standard deviation of group 2 over the sample size of group 2. and we add them together and take the square root of the whole thing. Then we take that and divide it into the difference between those two. So it's still standard error divided into the difference to give you the number of standard errors apart the two means are. So if this comes out to be 1.5, when you go to look up your t-value using the degrees of freedom, how do you calculate the degrees of freedom? For this situation, you use this ridiculous formula down here. Right? Okay, so now normally what you would say is, how with that, I'm just going to use the sample size, the smaller sample size -1. Very conservative. You know it's going to be more than that, right? The real degrees of freedom. SPSS will calculate the degrees of freedom in this situation, but you would just probably use a smaller sample size -1. So if this were 25, sample size 25, sample size 25, you'd say just at 24 is my degrees of freedom. That's very conservative. You know, and you could miss rejecting a null hypothesis when you could have, but it's still going to be close enough that you're going to say, oh, listen, I was so close to the t-score that, yeah, maybe it was just because I was very conservative with degrees of freedom. So you could go back and really calculate it carefully if you needed to. So you compare your critical value at t, which is based on the degrees of freedom and the table, and you compare it to the t that you calculated to see if the two means are far enough apart for you to reject the null hypothesis. Okay, and this is all practice. Do a problem, do the assignments, and when you apply this stuff, and really for the most part, you're going to be using SPSS to do this kind of stuff. You can also do this with proportions. With proportions, you're usually dealing with very large sample sizes, so you just use 1.96. Notice it says Z is equal to the difference between the two proportions over the standard error for the two proportions, right? So now remember when we only had a single sample, we're doing confidence intervals. What was this? What was the standard error when we use square root of p times 1 minus p over n, right? Take square root of that. So you're kind of doing that over here, right? Except you're doing it by pooling the two proportions, right? So, but I mean, you just apply these formulas. So that's the way we would deal with this stuff. That's how we determine whether we can reject the null hypothesis when we're comparing the means of two populations. So let's think about this. I'm comparing the means of two populations. Let me just get a piece of paper back. So now, that's not always the case though, right? So this works great. Let's say I'm doing a study. And in my study, I'm saying to myself, you know, I am going to, I know that the mean cholesterol level for French nuns is 190. They eat a lot of, a lot of foie gras, a lot of pate in France. They have a very high cholesterol level, 190. American nuns, they're vegetarians. We do a study.
No bias right now.
I'm making this stuff up as I go along. American nuns, they eat a much lighter diet, not so much rich food, no butter, the kind of stuff. So at any rate, American nuns, they don't go to McDonald's. American nuns, we don't know what there is. In France, the church in France tests all the nuns. They go for physicals every year. They test them all. And they know the mean cholesterol level for nuns in France. In America, we don't do that. We don't know what it is. But I want to know, is there a difference? Is that something we should be concerned about? How does it compare to French nuns? Well, we're not going to test every nun. We can't afford to do that. We're going to do a random sample of American nuns. So we're going to sample 100 American nuns. And we find that the average cholesterol level, given a sample of 100 nuns, is equal to 180. And the standard deviation for our sample of American nuns, actually, I'm not even going to do that. I'm going to say I know the standard deviation in France is let me make something up here, come up with something that 49. Standard deviation in France is 49, big number. Okay, so I'm going to say to myself, gee, that's very interesting. However, Actually, I'm going to make it smaller than that. I'll make it 25. Standard deviation is 25. So I'm saying to myself, I'm going to assume that the variability for American nuns is the same as is for French nuns. So I'm going to say that the standard deviation for American nuns is known and I'll call it 25. So in this situation, I can say, well, gee, I'm going to just say the X bar 1 minus the mean. In other words, what's our null hypothesis going to be? The mean for American nuns is equal to the mean for French nuns. And our alternative hypothesis, mean for American nuns, does not equal the mean for French nuns. However, I know what the mean for French nuns is, 180, right? So I can just put 180 instead of this here, or is not equal to 190, I'm sorry, 190, right? So now I have to check to see whether the mean, whether this is true or not. Can I reject this null hypothesis? Well, so how am I going to do that? Well, I'm going to say what's the difference in the two means? The mean that I got from Americans was 180 minus the mean I know for the French nuns is 190. So this, the top part of this, is 180 minus 190, which is 10, minus 10, but I'm not going to bother with that. Divided by the standard error tells me how many t-scores apart, how many standard errors apart that they are. So what is the standard error? Well, if we know the population standard deviation is 25, it's going to be 25 over the square root of the sample size, which is 100, right, which is 10, it's 2.5. So this is 2.5. So the t-score, or the z-score, right, I'm using z because it is, I know the population, I'm saying I know the population standard deviation is equal to 4. So what is the critical value of z? It has to exceed in order for my p-value to be less than 0.05. 1.96. Does it exceed 1.96? Yes, it does. So I can reject my null hypothesis. What if I didn't know the standard deviation? What if I didn't know the standard deviation and the standard deviation for my sample was 25, right? Well, now that's instead of using, it's still 25 divided by 10 is equal to 2.5, but I can't use z anymore. Now my critical value has to be t. T is going to be equal to, well, still 2.5 into 10. It's 4 if my standard deviation turned out to be 25. But now my critical value of t, remember my critical value for c was 1.96, but now t is based on my sample size, which is 24 degrees of freedom. So t is 2.064. Can I reject my null hypothesis still? Well, yes, I can, right? Because my number of standard errors apart, my t critical, my t value that I calculate is 4. I only need to exceed 2.06. Okay? Didn't change the outcome this time.
24 degrees of freedom, you said?
Yeah, because sample size was 25. Oh, I'm sorry, 99 degrees of freedom. Right? Sample size was 100. Degrees of freedom is 99. You're right about that. Okay, so then probably was more like 2.0, right? Is my critical value for t for that big a sample size. Well, that's nice. But what if my sample size was only, what if the difference between these two, let's say instead of 180, it was 185. So the difference between these two was only 5. And let's say my sample size was only 10, right? Let's say my sample size was 25. So that would be standard deviation is 25 divided by 25 square root of 25 is equal to 5. So now 5 is my standard error. So 5 over 5 is only 1. So I failed to reject my null hypothesis. Trust me, when you work on these, it'll be a little bit easier. It'll come to you as you play around with them. Now, the main thing is next we had to go, well, now if we got two samples, A and B, right? Population A and population B, our null hypothesis mu A is mu B, our alternative mu A does not equal mu B, and we would go and use our formulas that we had for two populations, and we would say T is equal to, and we would do our calculation. We would use one set of formulas if it were equal standard deviations, different set of formulas if it was unequal standard deviations in the two populations. But eventually, we would get around to looking up what T critical is, right? And whatever that is, say it's 2.04, our T that we calculate, right? Our T that we calculate, if it's more than 2.04, if they're further apart than 2 standard errors apart, we reject the null hypothesis. If they're not more than 2.04, we fail to reject the null hypothesis. Why? Because at that critical value, the p-value is the same thing as the alpha value. In other words, the probability of getting that extreme result is exactly 0.05. So we're looking to exceed that number. So the p-value goes below 0.05. It's less likely than 5%. So that's how we would do this if we were dealing with two populations. Okay, that's nice. But now, what about the situation where I might have, where, I'm going to do a survey of all the religious orders, all the nuns, all the Catholic nuns in the world, right? All different countries in the world. Okay, well, how many samples then do I got? I got America, I got France, I got Namibia, I got dozens, hundreds of countries, right? If I want to compare all of those means, X bar 1, X bar 2, if I want to compare all of mean for group 1 to mean for group 2, mean for group 3, and so on, I'm going to make this a little bit less ambitious. I'm just going to say for the US, France, and Germany. So how many groups do I have here? I got 3 groups. So I want to compare mean for US to the mean for France to the mean for Germany, right? So I could use the t-test to do that, right? How would I use the t-test? First, I would compare the mean for US to the mean for France. Then I would compare the mean for US to the mean for Germany. Yeah, but wait a second, I'm missing something. And now I got to do the mean for France for the mean for Germany, compared to the mean for Germany. I got to run the t-test 3 times. So each time I run it, there's a 5% chance of being wrong. That builds up. Well, what if I also included in this study the mean for Belgium, right? Okay, well now I got to do the mean for the US versus equals the mean for France. Mean for US is equal to the mean for Germany. Mean for US equals the mean for Belgium. But then I got to do mean for France equal to mean for Germany, and the mean for France equal to mean for Belgium, and the mean for Germany is equal to the mean for Belgium. Well, now look how it's multiplying. I'm getting a permutation of the number of means I got to compare using the t-test. So the t-test is not an adequate test for this. It's too laborious, number one, and it introduces error because we're repeatedly using the t-test, right? It's like Russian roulette, right? Put bullet in, you keep turning it and trying it every time. Eventually, you're going to lose, right? So we need another test. That's the analysis of variance. How does the analysis of variance work? Okay, so first of all, number one, what's the null hypothesis for an analysis of variance? I just gave it to you, right? I said, oh, the mean for group 1 is equal to the mean for group B. You're exactly right. You're about to get it right. Mean to group 3. I'm going to just stick with 3 for right now. What's the alternative hypothesis? You're tempted to say none of the means are equal to one another, right? That's not it. It's at least 2 of the means are different, right? Okay, so we don't need them to all be different. Just at least 2 of them are different. If we can establish that there's at least 2 of these that are different, then we can go back and take a close look and see which 2 are different, right? So that's what our analysis of variance is all about. Okay, so let's think about what might impact this. So what we want is we want to prove that these means are different from one another. So what would help us prove that? If the means of these three groups, let's say the mean, that we took the samples and the means for each of the groups were 90, 95, and 100. Or let's say instead they were 80, 120, and 200. Which of these two would you say is more encouraging in terms of the population means being different? Well, the bottom one, the means are further apart, it encourages you to say, gee, it looks like there really is a difference in these populations. Instead of 90, 90, or even worse, 94, 95, and 95.5. It doesn't look like looks like it'd be difficult to prove that these are different. These populations have different means. Here it looks like it's going to be easier to prove it. So the means being very different from one another, right? The distance being large between these means helps us. That's a good thing. What else helps us? Well, each time we're doing this in these three groups, we're doing this from samples from the three groups, right? X bar 1, X bar 2, X bar 1, X bar 2, X bar 3, right? We're doing this for three different groups. What also helps, if within these groups, that the numbers within these groups are very tight. The variability inside the groups is very small. That helps us also. So in other words, if the numbers, when we take sample of group 1, if the numbers come out to be, remember, I'm going to use 80, 120. Okay, if the numbers were 80, 82, 81, 79, and this one was 121, 119, 117, 122, and this one was 201, 205, I'm sorry, I think I put, 201, 205, 199, 200, right? Those numbers are very close together, right? So that encourages me to say, gee, within each group, there's a very narrow variance, and they're so far apart. It really looks like these three means are different from one another. On the other hand, if the numbers within this group were, instead of 80, 82, the numbers were 10, 200, 150, there's so much variability in this group, I'm less comfortable with the mean being really 80. And the same thing with 120, my confidence interval, so if this is, instead of like these being close together, this is 90 and 200 and 110 and 50. If they're so variable, my confidence interval for each one of these means gets wider, right? So I'm not so sure where the true mean is. So I want two things. I want the means of the groups to be far apart, and I want the variability within the groups to be narrow, right? So we actually can invent a statistic. We call it the F statistic, for analysis of variance. I'm going to play a video. This is my video. Okay.
That was a good video.
Oh, you saw the video already. I'm gonna play it right now. So if you guys have, yeah. Okay, let me get
I
the
didn't
point.
realize it was you.
Maybe that's because when I'm doing this on the fly, it's a lot different than if I can write it down and my thoughts on it. It's like, when the president talks without a teleprompter, things can go wrong, so. So it's the same thing with me, when I'm talking without a teleprompter, bad things can happen. Okay, let me see if I can't find this now. Let's see here. Okay, let me get to Blackboard again. How did I lose Blackboard? Okay, let's see.
I think Bloomberg is gonna get it right.
Oh, God.
I think he's gonna win.
I kind of like Bloomberg.
I think he's gonna win.
The thing about Bloomberg is he wasn't crazy. So he's a pretty stable guy
Yeah.
compared to most politicians. Yeah. Well, yeah, that's true. Yeah.
We don't, but we need someone who's gonna
Yeah, but as far as billionaires concerned, I mean, his public policy had a very strong health policy, who knows? Don't get us into politics now. This is statistics. Now we're getting into trouble. This is getting recorded here. God only knows what'll happen. Forget this. Forget this. But stop it right now. Stop this right now. We're not going any further with this. Okay, hang on a second here. Let me get into this thing here. Let me track down this video. Okay, so I think is it in here? Here we go. Okay, here it is. Okay. So I'm going to play this. This week, we're going to use analysis of variance to compare means again, except this time we're going to be looking at 3 or more groups. This past spring, I was lucky enough to get to the Brooklyn Botanical Gardens while the cherry blossoms were in bloom. And I noticed something very interesting. They filled an entire field with these beautiful cherry trees. If you ever get a chance to get there in the spring, so many of them, and they were so close together that it was hard to distinguish the blossoms from one tree from the blossoms from another tree. There were a variety of trees that were present at the Brooklyn Botanical Gardens. Some of the trees were wide and very full of blossoms. Others of the trees were much narrower. And I noticed that if the trees were very wide, if the blossoms were really spread out, that in order to be able to distinguish between individual trees, the tree trunks had to be very far apart. On the other hand, if the trees were very narrow, the trunks didn't have to be that far apart in order to distinguish between individual trees. I further noticed that the trees were symmetrical. The trunks were in the middle of the trees, and more of the blossoms were towards the center of the tree, fewer were far away from the tree. I realized that there's something else that has those same characteristics. I look at the normal distribution. It's bell-shaped so that the center is in the middle of the distribution, and more of the values are close to the mean, fewer are further away from the mean, and it's symmetrical. Here, we see 3 groups represented on the top and on the bottom. The variability is the same for all of these groups. On top, the means are close together, so it's hard to distinguish between the 3 groups. On the bottom, the means are further apart, making it easier to distinguish between them. Here, the means are the same, but the variability for the groups on the bottom is much smaller. So even though the means are the same, we can distinguish easily between the 3 groups in the bottom set. Let's create a new statistic that we're going to call F. F is going to be the ratio of 2 numbers. On top, the numerator is going to be the variance between the means in several groups. The larger the variance between the means of the groups, in other words, the further apart the means are, the larger that ratio F is going to be. On the bottom of this ratio, we're going to put a number that represents the variance within the groups. As the variability within the groups becomes smaller and they become narrower, F also becomes larger. Our statistic F represents a ratio of the variance of the means over a number representing the variance within the individual groups. The further apart the means are, and the narrower the groups are, the easier it is to distinguish between the groups and the larger the value of F. F has a probability distribution associated with it. In this graph, we can see that there's a region that if F is large enough, we can be safe in saying that the means of the groups are different rather than being from the same population. Our lab exercises this week, we're going to use the F statistic to determine when we can distinguish between means of 3 or more groups. In this chapter, you'll find a demonstration of using Excel to calculate the F statistic or analysis of variance. You'll also find a demonstration of using SPSS to do the same thing. Okay, I'm safe now. Okay, skewness Earlier in the semester, when we talked about the normal distribution, a perfect normal distribution, right, has certain properties, right? So it's bell-shaped, and that bell-shaped property is a consequence of the fact that the mean, the average, is in the center, and the median is the same as the average. In other words, the middle value and the average value are the same. And as you get further from the mean, let's say that this is the average weight of male students. Let's say average weight is 150 pounds, right? So as you get further from the center, you get fewer and fewer people that are in that category. Like if this, instead of a curve, if this were a histogram, the bar would be lower. So there are going to be people that are 140 pounds, and there are going to be people that are 160 pounds, but not as many as are between those two numbers that are 150. And there are going to be people that are 130 pounds, and also people that are 170. But now, as you get further and further from the middle, you get fewer and fewer people in this population that meet that criteria, right? That gives us this bell-shaped curve. And it has a particular mathematical formula that represents this curve based on chance. This is really based on chance, whether or not you would find someone in any part of this. Okay, so now, in some situation, you have distributions that aren't really normal, that are skewed. So in other words, you could have a population, for instance, let's say the average salaries for professors in CUNY. And that might look something like, let's see, might look something like this. Okay. Okay, where the mean is, let's say the mean is nice number, like 100,000, right? Nice, big, chunky number, right? Okay, so let's say it's 100,000. Okay, so, you know, the administrators are up here. Maybe they're making 130,000 or something like that, or really big shots that are pulling in, doing research, pulling in a lot of money and stuff like that. They're up here. But then it's, look, we have a lot of people that are much lower than the average. So the median gets pulled to the left of the, in other words, 50% of the people are in here, 50% are up here, but the median's pulled away from the average. People making a lot of money pulling up. So these might be adjuncts, part-timers, stuff like that. So if you include all the salaries, it might be skewed like this, right? Also premature births, right? So the average birth weight of infants might be, what's the average birth weight in ounces? 16, 10 pounds would be 160, maybe 140 ounces, right? So, but a really big baby is what, 160, right? So you're not going to get many babies that are more than 160 ounces, right? But you may get a lot of premature births where the weights are 20 ounces or 25 ounces or something like that. So it isn't really a normal distribution. This is skewed. In this case, it's skewed to the left or negatively. So the mean and the median are not in the same place. The median gets pulled down. Okay, let's say that we have a situation where we're looking at the average Xerox employees, their average salary, and we have a situation like this where this is what it looks like, and then it's skewed like this. Well, what does this mean? It means that there's some people, a small number of people, making a lot of money. That could be the CEO, the CFO, the division presidents, and so on and so forth. But the rest of the company is kind of down at this end. So what happens there? Well, the mean, the average is pulled up by these very high salaries. But that's only a few people, so the median doesn't move much, right? So the mean gets pulled away from the median up. So that's positively skewed, positively or right skewed. So that's what we mean by skewed, that it's not really a normal distribution. One of the properties of the central limit theorem is that if you take a skewed distribution, and here is this is the average, and this is the median. Okay. If you take a sample from this population, you take repeated samples from this population. Okay, well, if you just we're going to sample one person, if we take samples of size 1, well, you're more likely you're going to wind up with somebody above the median than below the median. Well, you're going to find up somebody. You're going to wind up with someone. It's just as likely you'll find someone below the median as above the median, right? Why is that? Because 50% of people are below the median, 50% are above the median, right? However, it's more likely that you're going to find someone that's below the average than above the average, right? So your sample, with a small sample size, your sample distribution is going to be skewed also. But as your sample size gets bigger and bigger and bigger, well, the fact that you are taking samples means that you're going to get closer and closer to a 50% on either side of the median. So you're going to wind up with your sample distribution, as the sample size gets bigger, becomes less and less skewed. So even if the population is not perfectly normal, your sample distribution can be normal, right? So part of the nice thing about central limit theorem is as your sample size gets to a decent size, you don't have to worry anymore about the population distribution being perfectly normal. It's okay for it to be skewed a bit, but you can still depend on the central limit theorem and your confidence interval and your t-test to work properly, because this tells us that we still will get a normal distribution if our sample size is big enough. And the sample size most people say is sufficient to avoid problems with a population that's not perfectly normal is about 30. That's why in a lot of books they'll say when they refer to a large sample size, they'll use 30 for a large sample size. So let me move on to okay, let me move on to calculating analysis of variance. So now I'm not going to do it here, but if you look at the second video is going to take you through.
I've created 3 simple
a
groups
demonstration of calculating analysis of
the
variance.
F statistic. First group has 5 values. Second group has 5 values.
You know what, I'm going to do it. You can watch
and
the
last
video on
group
your own.
has
I'll
5
actually do it here.
values.
And then I'm going to repeat it
Use the
using
analysis of variance to
SPSS.
determine whether the populations
Stop.
that these
Stop
samples
talking.
were taken from have.
Okay, let me get rid of this. What the hell? Where'd I go? Okay. No, okay, let's open this. Okay, open in Excel. Remember, the way that this works is that we are going to compare the variability between the means versus the variability within the groups, right? So we want the variability within the groups to be small, the variability between the means to be big, to give us that ratio. So I got 3 groups there. They named Fred, Jim, and Alice, just to give them names, right? But these are the values that they are. These are these numbers. I'm going to copy them down here so I can work with them. And Jim, Jim's going to go down here. And Alice. This is going to be, you can just look at this as group A, group B, and group C. And these are the values, the samples that we took. Maybe they're workers that work with Alice. Maybe it's the worker's performance on some test or some task. So first thing I want to do is I want to look at the average for each of these groups. So I'm going to calculate the average for this group is turns out to be 1.8. The average for this group turns out to be 3.4. Average for this group turns out to be 4.4. Okay, so that's the average for this first group is 1.8. Average for the second group is 3.4. Average for the third is 4.4. So what's my null hypothesis here? Mu1 is equal to mu2 is equal to mu3. In other words, the mean for the true average for Fred equals the mean for the true average for Jim, mean for true average for Alice, right? So now I'm going to take these means, that 1.8, I'm going to put it here, equals, so now I'm going to do this way. I'm going to put in the dollar signs because I want the absolute value. This is literally what we did at the beginning of the semester to calculate the variability, calculate standard deviation. Okay, I'm then going to copy this down. Okay, I'm going to do the same thing here is equal to X bar for this group is equal to 3.4. I'm going to copy it down.
That absolute value just keeps it in one spot.
Yeah, exactly. It's called when you allow it to move, it's called relative addressing, and when you don't allow it to move, it's called absolute addressing.
Right, if it will go from like 1.8, 1.9.
Yeah, exactly. Otherwise, it just go down.
Yeah.
Yeah, so this is a handy way to make sure it doesn't do that. Okay, I'm going to carry this down. Okay, so I'm going to calculate my variability here. Okay, so I'm going to take the difference between each value for this particular group and the mean for that group. Oops, equals this minus this. Okay, that's the difference. Okay, and that's the differences. I'm going to square the differences. This times itself. That's the square of the differences between each one of these values. Okay, and then I'm going to add all of these together. And what is that called? That's called the sum of the squares of the differences. And what do we do with that? Usually what we do with that is we divide by the sample size, take the square root, and that gives us the standard deviation. But right now I'm happy just getting the sum of the squares of the differences. I'm going to do the same thing here. Okay, and copy this down. Okay, I'm going to add these together. So automatically I can see right here, look at this, the differences between the values and the differences, is this right? 3.4. No, something's wrong here.
Yeah,
Equals 5 minus 3.4. Yeah, there we go. Okay, that's better. Okay, so the differences, the sum of the squares of the differences is bigger for this group, Jim, than it was for Fred, for the other group, right? So there's more variability in this group than there was in this group. Okay, so let's do this for the last one. Times itself. So the sum of the squares of the differences are calculated for each one of these. Okay, so let's see what we got here. So our statistic is going to take our F statistic is going to be the average sum of the squares between the means over the average sum of squares within the groups themselves. So this top part is the average of the sum of these squares 2.8, 5.2, and 17.2. Okay, so if I go over here, the sum of the squares of the differences between the groups is, let's see, sum of squares, sum of the differences between the means. Wait a second here. The sum of the squares okay, hang on. Sum of the squares of the differences between the means. Uh-oh, somebody waved their arms. There we go. Okay. Okay, so this is going to be equal to, I think it's going to be equal to the average of the sum. Mean sum of squares between the average of these three numbers, 2.8 plus 5.2 plus 17.2. It's 25.2. Okay, so number of degrees of freedom, well, actually, I should have just added them together, equals 2.8 plus 5.2 plus 17.2. And I'm going to divide that by the degrees of freedom, number of groups minus 1. There's 3 groups, that's going to be 2, minus 1 is 2. And that comes out to be 12.6. So the mean sum of squares between the groups is 12.6. That's the average. See, this is the sum of squares. This is the variability. This is the sum of squares. Oh, I'm sorry, I did this wrong. This is the sum of squares within the groups. It's 25.2. Yeah. Okay, good. Okay. So let me go back to this. Yeah. Actually, it actually copied it up over here. So okay, good. I got it. All right. So this 25.2 is equal to the sum of these, of the 2.8 and the 5. You know what it is? I never pulled all the way down, so I was looking at the whole thing. 2.8 plus 5.2 plus 17.2 is the sum of squares of the differences within the groups, right? Within all of the groups, all added together, 2.8, 5.2, and 17.2. The degrees of freedom is the number of subjects minus the number of groups. Number of subjects is 15, 3 groups, so that's going to be divided by 12 to get the mean sum of squares within the groups. And that's the bottom part of this ratio. That's going to be, that's the average sum of squares, the mean sum of squares within the groups, within the individual people in the groups. Okay, and we got that by adding up the sum of squares for this group and the sum of squares for this group, sum of squares for this group, and dividing by what's basically the degrees of freedom. Okay, so now I have to find the degrees of freedom. I have to find the mean sum of squares between the averages of these groups. So the overall mean is 3.2. Where did that come from? That came from the average of 1.8, 3.4, and 4.4. Right? So the average was 3.2. The individual means are 1.8, 3.4, and 4.2. So the overall means are 3.2. So the differences between the individual means for each group and the overall average for all the groups is minus 1.4, 0.02, and 1.2. I squared the differences for each of those, and it's 1.96 and 0.04 and 1.44. And I also now at this point, I'm also making sure that I account for whether or not they have equal sample sizes. So I multiply by the number of people in each group, and the differences and the sum of the squares of the differences for each one of these between the mean and each individual group's mean is 9.8, 0.2, and 7.2. So the sum of the squares of the differences between all of the means is equal to 17.2. So this number becomes 17.2. And then I divide by the number of degrees of freedom, which is the number of groups, minus 1. So there's 3 groups, right? So minus 1 is 2 degrees of freedom, and that comes out to be 8.6. So
What's the difference, the degree of freedom different on the second part than the first part?
because this is between the means. This is the
I think the averages are
because I'm only working with 3 numbers, right? The means of the 3 groups,
the
right?
first one.
And the first one, I'm working with all of the people, which is 15 people, right? Minus 1 for each group, right? So it's 15 minus 3. Yeah, I know, it's a little confusing, right? Well, that's okay because we're hopefully never going to do it this way, right? Right, this is a demonstration of it. Okay, so now what do we wind up with here? We wind up with the F statistic being the average sum of squares between the means, which was 8.6, right? That's what we found here between the means. And the mean sum of squares within the groups was 2.1, and that average comes out to 4.09. Do we want that to be a big number or a small number? We want the difference between the means to be wide, and we want the variability within the groups to be narrow, so it's easier for us to tell that there's a difference between the means, right? So we want that number to be as big as possible. So 4.09, how big is that? Is that big enough for us, right? Well, now we have to go to our critical values for analysis of variance in order to be able to tell whether that is big enough to reject our null hypothesis. So how does that work again? Well, the idea here is that let's see, I need my pen. Okay, the idea here is that here is what my F value could be. My F value can be 0, right? The top part could be very small and the bottom part could be very big. My F value could be 0, right? Or it could be a big number. It could be 5, it could be 10, and so on and so forth. It's the ratio of those 2 numbers between the means and within the groups, right? Ratio is 2 numbers. The probability of it being 0 is pretty low, right? So, because in order for that to happen, you'd have to have all those means being exactly the same, right? Not going to happen very frequently. Even if there's the null hypothesis is true, the chances of that happening are pretty small. So this probability is pretty small. So even if remember that this is the probability of the null hypothesis being true. So if the null hypothesis is true, it could be 0, but it's not very likely. But it's going to be a low number because we wouldn't expect the means to be very different from our samples. Now, as we got further, as this F value gets bigger and bigger and bigger, right? The probability we would get that big a value if the null hypothesis is true goes down because we wouldn't expect the means to be so far apart and the variability to be so small that we wouldn't expect, if the null hypothesis is true, we wouldn't expect to be that different, for these things to be that different from one another, right? So as the F score goes up, we become less likely that the F score will be, that the null hypothesis will be true as the F score gets larger. Okay, so in order to determine for our sample sizes, right, we have 2 sample sizes here. We have number of groups and we have the number of people in the groups. There's 2 sample sizes here. We have to go to our analysis of variance, critical values for analysis of variance. Press the ANOVA. See if I can't get the table. Okay, here's the table. Oh, didn't open. Okay, here's our analysis of variance. And this is going to just take one more second. Our analysis of variance, the distribution, we have 2 degrees of freedom. One is for the number of groups, right? So the number of groups is 3, minus 1 is 2 degrees of freedom. So we're going to use this second column. And the other one is for the sample size, the actual people within the groups, which is 15 minus 3 would be 12. So if I look here, my critical value is 3.89. 12 versus 2, 3.89. So critical value is 3.89, right? So 3.89 is the point at which there's only 5% chance that we would get that big an F score if the null hypothesis were true. So if you get a value that's bigger than that, there's less than a 5% chance of the null hypothesis being true. 4.09, right? So we reject the null hypothesis, right? That these three means are different from one another.
I'm sorry, can you repeat that?
Sure. So the distribution for ANOVA, it takes this shape. The bigger the F value, the less likely that your null hypothesis is true. So in our particular situation, the table told us the critical value of F was 3.89, which means that if you have a value bigger than 3.89, it's in the top 5% of this curve. There's less than 5% chance your null hypothesis is true if you're bigger than the critical value, right? That's the 5%. In other words, if you're bigger than 3.89, there's only, say, if you're at 4, there might only be a 3% chance that the null hypothesis is true. If you get to 5, there might only be a 1% chance that the null hypothesis is true. So the bigger the F is, right? The bigger the F is, the less chance that the null hypothesis is true. But the real number you have to exceed is the critical value, which is based on your sample, the number of groups, right? And the number of people within the groups, those 2 degrees of freedom. Okay, and that's where you got that. We got that from the table. The intersection of those 2 groups was 3.89. So our actual F value was calculated to be I don't remember what it was, but about 4.09. Our critical value is 3.09. So since our F value that we calculated exceeds our critical value, then the probability that we would get this big a difference is less than 5% chance, which means that since P is less than alpha, alpha was 0.05, P is less than alpha, we reject the null hypothesis that the 3 means are equal. Do we know which 2 means are different? At this stage, we don't. All we know is that we can say that the 3 means are different from one another. If we want to be able to predict which of the 3 means are not equal to each other, we have to do a different test called the post hoc tests. That's in that video. There's a point there where I'm going to take this. Let's give me one more second. Oh shit! Excuse me. I'm getting frustrated because it's taking me so long to get through this. So I want to do one more test. Indulge me for a second.
So post hoc means after?
After the fact. In other words, after you've proven that you can reject the null hypothesis, and only then you run the post hoc tests, right? You don't run the post hoc tests until you're sure you can justify it. Okay. Okay, where is it? Here we go. And okay, SPSS. Please open the right version of it. I'm going to save it anyway. My desktop. Let me get all these out of the way. No, it opened the wrong version. Let me open the right version and navigate to it. Just give me one more second. I can do this really quickly once this ridiculous program opens up. Come on. Finally, okay, good. Say open, data. I'm gonna go to, no. Yeah, here it is. These are the same numbers. Okay, so what am I gonna do? See, there's the 3 different groups. That's Fred, Alice, and whatever. I'm gonna go to analyze, and I'm gonna go to compare means, because that's what I'm doing. I'm still comparing means, even though it uses this analysis variance. And my dependent variable is the actual measurement itself, and then my vector variable is the groups. Okay, so I'm going to click OK. Oh, I didn't. That was an analysis variance. Excuse me. Analyze. this compare means, one-way analysis of variance. My measurements go in here. My groups go into the factor group. I say, okay, it does my analysis of variance, and it comes up with the F-score we just found, 4.095. See, the mean square between is 8.6. Mean square within the groups is 2.1. Divide one into the other gives you the F-score. All of these numbers are the same numbers that you saw us do before, 17, 25, 42. And the significance, the probability of getting this outcome is 0.04 if the null hypothesis is true. That's less than 0.05, so we reject the null hypothesis. Since we reject the null hypothesis, we can go back here and say, compare means, one-way analysis of variance, except this time, yeah, because it's bigger than F critical, but also the significance is less than 0.05. You don't need to know what the critical value is. Since SPSS tells you there's less than 5% chance of being wrong if you reject the null hypothesis. Now I click on the post hoc tests. Now there's a lot of different post hoc tests you use in different situations. Usually you can stick with just Bonferroni or Tukey. I'm going to use Bonferroni. You could use either one of those two. They're relatively conservative. That's one good reason for using them. Okay, and then I click OK. Now it gives you this result, which actually compares them group by group. So if you compare Fred to Jim, the significance is 0.31, bigger than 0.05. I can't say that those two means are different. Fred to Alice, 0.045. I can say that those two are different. Those two means are different. And in fact, it looks like Alice and Fred are the only two here that are different from one another, because all the other p-values are greater than 0.05. So that's how you use the post hoc test to determine which of the means are different. But you only use that once you've been able to reject the null hypothesis that they're all the same. Okay, we have to get out of here before the lights go out. Okay, guys, we have this whole exercise is on those videos, a series of 4 videos, and they'll show you the post hoc tests and stuff like that. And and the person doing that one won't be rushing.
Alrighty, thank you.
Okay. Okay. Good night, guys online.